In the 1840s, American railroads obsessed over speed and size, dismissing one radical locomotive as a joke: too slow, too small, too strange to matter. Yet within decades, this so-called tiny wheel 080 could haul loads that bigger engines could not budge, shattering the industry's own logic. Why did a design mocked as obsolete become the secret backbone of freight movement? And what flaw in railroad thinking did it expose? To answer that, you have to go back to the machine and the inventor everyone tried to ignore. In railroad engineering, numbers tell the story before a single wheel turns. The 080 designation comes from the White notation, a system that breaks down a steam locomotive's wheel arrangement into a quick code. The first number counts the leading wheels, those small unpowered wheels at the front that help guide high-speed trains around curves. The second number is the count of driving wheels, the big powered ones that grip the rails and do the real work. The third is the trailing wheels, which support the firebox at the rear. For the 080, the math is stark. 0 leading wheels, 8 driving wheels, 0 trailing wheels. Every bit of the engine's weight presses down on those 8 coupled drivers, maximizing traction. This setup stands in sharp contrast to the glamorous passenger engines of the era. Those machines boasted 6 or even 8-foot driving wheels, sometimes taller than a grown man. Their massive wheels were built for speed, spinning fast and smooth over long distances. The 080, by comparison, rolled on driving wheels just 4 to 5 feet in diameter, typically 50 to 56 inches. To the untrained eye, these wheels looked comically small, almost like the engine was built for a child's toy set. But the size wasn't a mistake. Smaller wheels mean more torque at low speeds, allowing the locomotive to start heavy trains without slipping. No leading or trailing trucks meant the 080 could put all its weight where it mattered most, directly over the drivers. This made it ideal for jobs that demanded brute pulling power rather than velocity, tasks like moving long cuts of freight cars in crowded yards or dragging coal up steep grades. The White Code, then, isn't just a label. It is a blueprint for how the locomotive works, and a clue to why those so-called tiny wheels would soon upend the industry's ideas about strength and utility. Ross Winans didn't look like a man out to change the rules of American railroading. He was a machinist by trade, hired by the Baltimore and Ohio Railroad in the 1830s, and known for a stubborn streak as much as for his technical skill. In 1844, when the Baltimore and Ohio Railroad faced the challenge of dragging ever heavier coal trains over the brutal grades of the Alleghenies, Winans offered a solution that defied the era's obsession with speed. His idea was simple but radical. Forget about leading wheels for guidance or trailing wheels for balance. He built a locomotive with 8 coupled driving wheels, all clustered beneath a squat, powerful boiler. Every pound of weight pressed straight onto those drivers, squeezing every bit of friction from the rails. The first of these engines, weighing in at 19.5 tons, rolled out of the railroad shops that same year. Its cylinders measured 14.25 by 24 inches, a size chosen not for high velocity, but for the raw muscle needed to start a fully loaded coal train from a dead stop. The engine's wheels, just over 4 feet in diameter, looked almost comical beside the towering drivers of the day's passenger locomotives. But Winans wasn't interested in appearances. He wanted traction, not glamour. The railroad quickly saw the practical value. Over the next few years, Winans and his team produced more than 200 of these engines for the railroad. They became the backbone of the railroad's mountain operations, earning a reputation for hauling loads that would leave lighter engines spinning helplessly on the rails. By the late 1840s, even outside builders like Baldwin were supplying similar designs, though none quite matched Winans' knack for putting every ounce of weight to work. In an industry dazzled by speed records and gleaming passenger trains, the 080's blunt force approach was a quiet revolution. One born not in a boardroom, but in the hands of a machinist who saw the physics of the problem more clearly than anyone else. Tractive effort is the heart of what makes a locomotive pull, and it all comes down to how force moves from the engine to the rails. Imagine a steam locomotive's pistons pushing on rods that then turn the driving wheels. The size of those wheels is not just a matter of style, it is a lever arm, and it controls how much grunt the engine can deliver at the rail. With large wheels, every piston stroke covers more ground, but the force delivered to the rail is spread out. That is perfect for running fast, but not for starting a heavy load from a standstill. Smaller driving wheels flip this equation. When the piston pushes, the shorter radius means more of that force goes straight into turning the wheel with power, not speed. In physics terms, torque, the turning force, rises as the diameter falls. For the 080, those 50 to 56-inch wheels acted like a wrench with a short handle, harder to spin fast, but able to twist with far more strength. It is the same reason a mechanic grabs a breaker bar for a stuck bolt. The smaller the circle, the more easily the engine can get a heavy train moving. But torque alone is not enough. The real magic happens when weight meets friction. Every pound pressing down on the 8 driving wheels increases the grip, or adhesion, between steel wheel and steel rail. That is called adhesive weight, and it keeps the wheels from spinning uselessly when the engineer opens the throttle. With no leading or trailing trucks, the 080 puts every ounce of its mass right where it counts. The result is a locomotive that can push its tractive effort right to the edge of what the rails will allow before slipping. There is a simple relationship at work. Tractive effort climbs as driver diameter shrinks, all other things being equal. For example, the USRA 080 with its 56-inch drivers and 200 pounds per square inch boiler could produce around 49,000 pounds of tractive effort. Put those same cylinders on a locomotive with 72-inch wheels, and the pulling force drops by nearly a quarter. The math is straightforward, but the effect in the yard is dramatic. Engines with big wheels might look impressive, but they cannot match the raw pulling power of a purpose-built switcher with smaller drivers and all its weight pressing down on the rails. This is not just theory. Railroads measured tractive effort directly, weighing engines and calculating how much force they could apply before the wheels slipped. The 080's numbers did not just look good on paper. They translated into real-world muscle, especially at the low speeds where switching and heavy freight moves happened. In the world of steam, where every train is a battle against inertia, it is this balance of force, leverage, and weight that decides what an engine can actually pull. Adhesion isn't just a matter of brute weight, it's about how that weight is put to work. On a locomotive, every pound pressing down on the driving wheels translates into friction, or grip, between steel and steel. The 080 did not waste a single ounce. With 8 coupled drivers and no leading or trailing trucks siphoning off mass, the entire heft of the engine pressed directly onto the railheads. This was not a theoretical advantage. In switching yards and on steep grades, the difference played out in real time, train after train. Engineers talked about the factor of adhesion, a simple ratio that compared the weight on the drivers to the maximum pulling force before the wheels would slip. For steam locomotives, a factor of adhesion between 4 and 5 to 1 was considered ideal. Go below that, and the wheels would spin uselessly. Go much above, and you were carrying dead weight. The 080 lived right in the sweet spot. With all its weight on 8 wheels, it could apply as much tractive effort as the rails could bear, right up to the edge of slipping, but rarely over it. Picture a typical USRA 080, about 200 tons of locomotive, every pound pressing onto those 8 drivers. That is roughly 362,000 pounds of adhesive weight, all working to keep the wheels locked to the rails. with a tractive effort around 49,000 pounds. The factor of adhesion lands comfortably at 4.6. By comparison, a passenger engine with its weight split between drivers and trucks might see only 60 or 70% of its mass doing useful work, with a factor of adhesion sometimes drifting too low for confident starts. The effect was most obvious in places where the rails were slick with grease, rain, or yard dust. On a bad day, even the best engineer could find his locomotive spinning helplessly, the wheels shrieking against the track. With the 080, that scenario was rare. The broad spread of 8 wheels meant the weight and the friction were distributed evenly, lowering the risk of any one axle losing grip. In practice, this meant the engine could start heavier trains, recover from minor slips, and keep moving loads that left larger engines that were lighter on their feet stuck. Railroads learned to trust the numbers. The load distribution across 8 axles did not just prevent slippage. It also reduced the strain on rails and wheels, lowering maintenance headaches. The science of adhesion turned what looked like a limitation, small wheels and squat profile, into a decisive advantage. Every time the throttle opened and a heavy cut of cars began to move, the 080's design proved that the real contest was not about size or speed. It was about how much useful work could be wrung from every pound of iron, every inch of track, and every turn of those so-called tiny wheels. As yard crews prepared for the next round of switching, the numbers were not just theory anymore. The 080's grip on the rails was something you could measure, feel, and depend on, right up to the point where engineers and managers alike started to wonder just how much these engines could really handle. In the heart of a busy yard, the question of theory versus reality came down to a single test. Railroad officials gathered along the tracks as 2 engines lined up for a direct comparison. A standard road locomotive with its tall, impressive driving wheels, and a 080 switcher with a compact, unassuming profile. Yard logs from the early 1900s record the details, with weathered clerks noting train numbers, cut lengths, and the weight of each load. The challenge was simple: move a string of steel freight cars, each one heavier than what most engines handled on an ordinary day. The larger engine went first, its wheels spinning against the rails as it strained to budge the train. Despite its size, the load barely shifted. Observers, including mechanical superintendents and skeptical engineers, watched as the throttle was eased back and the attempt was abandoned. Then the 080 took its place. With every pound of its weight pressing down on 8 coupled drivers, the engine gripped the rails and began to pull. The pistons moved with slow, deliberate power. Inch by inch, the heavy cut of cars started to roll. Within moments, the entire train was moving at a steady crawl, 5 miles an hour, then 6 miles an hour, the load under control and the wheels never slipping. The yard's performance logs from that day show the numbers. The 080 moved a cut that weighed over 2,000 tons, a figure that had left the larger locomotive defeated. Word of the demonstration spread quickly. Mechanical officers who had doubted the value of small wheels now found themselves recalculating what mattered most in a switching engine. The test did not just settle a technical debate. It rewrote the expectations for what a switcher could do. In the eyes of the men who witnessed it, the pulling power of the 080 was no longer just a claim on paper. It was a fact, proven on the rails in front of those who mattered most. World War I brought a new kind of order to American railroads. In 1918, the United States Railroad Administration stepped in, determined to streamline locomotive production for efficiency and cost savings. The administration didn't just endorse the 080, they made it the official heavy switcher for the entire country. Their engineers drew up a standardized design, balancing every detail for maximum pulling power and reliability. The plan worked. Within 2 years, 175 080 locomotives built to the administration's design rolled out of factories like Alco, Baldwin, and Lima, and were assigned to more than 20 railroads. New York Central alone received 25, with subsidiaries pushing the total over 70. The real proof came after the war, when private railroads ordered more than 1,200 copies of the administration's pattern. These engines weren't just filling a niche, they were rapidly becoming the backbone of yard operations nationwide. The numbers tell the story. A single 080 could handle switching duties that once required 2 or even 3 older engines. That meant fewer crews, less coal burned, and reduced wear on both locomotive and track. In the largest yards, operational costs dropped as the new switchers replaced mixed fleets of outdated 060 locomotives and repurposed road engines. The Chesapeake in Ohio, for example, ordered 65 improved 080 locomotives in 1930, then expanded with another 125 for its Père Marquette subsidiary. These investments weren't driven by theory. They were justified by payroll ledgers and fuel receipts. The administration's standardization didn't just simplify maintenance and spare parts, it allowed railroads to scale up, putting more power on the rails for less money. The 080's utility was no longer a question of physics or theory. It was a matter of economics, proven in every yard where one engine now did the work of many. Steam faded from American railroads in the decades after World War II, but the 080 endured, refusing to disappear quietly. While streamlined passenger engines and new diesels took the spotlight, these switchers kept working deep into the 1950s and even the early 1960s. Railroad rosters from that era list dozens of 080 switchers still shuffling cuts of cars in major yards, their small wheels turning slowly under loads that would have challenged newer engines. Norfolk and Western's Roanoke shops built the last American steam locomotive for a Class I railroad in 1953, and it was a 080. On the other side of the country, Illinois Central and Chesapeake in Ohio held on to their switchers through multiple technological shifts, finding that nothing matched the raw grip and steady pull needed for yard work. Some of these engines survived long enough to find new homes. Republic Steel No. 285, built by Alco in 1925 as a USRA pattern switcher, worked through the steam era and beyond, switching steel cars until retirement. Today it stands preserved at the Kentucky Railway Museum. Its 8 coupled drivers and compact frame, a reminder of the design's staying power. Maintenance logs show No. 285 in service well into the twilight of steam, outlasting more modern types that were supposed to replace it. The story of No. 285 is not an outlier. Across the country, museum rosters and builders' plates tell the same tale. The 080 design's so-called tiny wheels proved durable, reliable, and indispensable right up to the end. In a world that moved on to faster, flashier power, the 080 endured, quietly doing the hard work year after year. Today, efficiency often hides behind convention, just as it did when tiny wheels defied railroad giants. As industries chase bigger, faster, or louder, the 080 locomotive's triumph reminds us that real progress favors function over hype. In a world still quick to dismiss the unconventional, sometimes the smallest wheels drive the biggest change. What overlooked idea might be waiting to pull more than we imagine? Share your thoughts below.